Today we're going to look at how we can construct RG graphs. Recall that an RG graph is an R regular graph with girth G, while an RG cage is an RG graph with the fewest vertices. It turns out that for every choice of R and G greater than or equal to 2, there exists an RG graph, and this implies that there exists an RG cage. In this video, we're going to be looking at a slightly simplified version of the original construction that was used to prove that there is an RG graph for any RG greater than or equal to 2. We're going to prove, using a variant of induction, that for any RG greater than or equal to 2, there exists a regular graph with degree R, girth G, and that contains a Hamiltonian cycle. At this time, it's not obvious why we would want our graph to be Hamiltonian, but the utility of this will be clear later. To make things easier, during this proof, when we say RG graph, we'll really mean Hamiltonian RG graph. As our first base case, there exists a graph satisfying our three properties with girth 2 and any degree R. In other words, the R2 graphs exist. We call these graphs the generalized digons. Next, let's call this base case 2. There exists a graph satisfying our three properties with degree 2 and any girth G. In other words, the 2G graphs exist. We call them the cycle graphs. Next, let's induct on girth. Our first inductive hypothesis is that for all G strictly less than an integer y, which is greater than or equal to 3, the statement for all R greater than or equal to 2, there exists an RG graph is true. We want to show that this implies the truth of the statement for all R greater than or equal to 2, there exists an RY graph. To show that the existence of RG graphs for girth less than y implies the existence of RG graphs for girth equal to y, we're going to perform induction again, this time on degree R. The result of this second induction will be that for any R greater than or equal to 2, there exists an RY graph. Recall that base case 2 tells us the existence of the 2y graph for all y, which is the cycle graph with y vertices. Our second inductive hypothesis is that for all R less than an integer x, which is greater than or equal to 3, the statement there exists an RY graph is true. So, by this inductive hypothesis, we know that an x minus 1 y graph exists. We'll call this graph A. However many vertices it has, call that number m. Then by our first inductive hypothesis, we also know that an m y minus 1 graph exists. Call that graph B. And now here's the coolest part of this proof. We can use these two graphs to construct an xy graph, which by our inner induction means that we can construct the RY graph for any R greater than or equal to 2, which then completes our outer inductive step, proving that we can construct an RG graph for any RG greater than or equal to 2. Here's an outline of what we're doing in this proof. Moving on to this construction, we're going to create a graph C from the graphs A and B. We want C to be x regular with girth y. Let Z be the number of vertices in graph B, and remember that B and A are Hamiltonian. Let little b sub 1, little b sub 2, and so on be a Hamiltonian cycle in graph B. For each distinct vertex b sub k in this cycle, generate a copy of graph A. Call this copy A superscript k, and take the disjoint union of all of these copies. We'll call this graph C. Recall that A is also Hamiltonian, so we can visually represent each copy of A with its Hamiltonian cycle. Now, so far in graph C, All of the vertices have degree x minus 1, as graph A was x minus 1 regular, and the girth is still y. Next, we're going to add some edges between copies. For any two copies that correspond to consecutive vertices in the Hamiltonian cycle of graph B, we link the last vertex in the first copy's Hamiltonian cycle to the first vertex in the next copy's Hamiltonian cycle, and repeat until we link the last vertex in the last copy's Hamiltonian cycle to the first vertex in the first copy's Hamiltonian cycle. Let's take a step back and think about the structure of this graph again. All of the vertices that are either the first or final vertices in the Hamiltonian cycle of each copy have degree x. The rest of the vertices in each copy have degree x minus 1. Also, the entire graph is Hamiltonian with the following Hamiltonian cycle. The girth is still y, because the girth of each copy of A is y, and the only cycle that goes between different copies is the Hamiltonian cycle across our entire graph C, which exhausts all the vertices in each copy, meaning it has length greater than y. Let's move on to the final step in our construction, which will raise the degrees of the rest of our vertices to x. Note that in each copy, there remain m-2 vertices of degree x minus 1, where m is the number of vertices in graph A. Also, remember that every vertex in graph B was defined to have degree m. So when we consider only edges that are not in our Hamiltonian cycle in graph B, every vertex in graph B is incident to m-2 of these edges. Keeping these facts in mind, for every pair of vertices b sub I and b sub j in graph B that are adjacent through an edge not in our Hamiltonian cycle, join some vertex of degree x minus 1 in copy I of graph A to some vertex of degree x minus 1 in copy j of graph A. In other words, for each edge in graph B that's not in graph B's Hamiltonian cycle, we produce an edge between the copies of A corresponding to the endpoints of that edge. Specifically, we add this edge between two vertices of degree x minus 1 in those copies. Note the requirement that the vertices be of degree x minus 1 excludes the first and final vertices of each copy, which have already been given degree x. Also, note that this final step does not always produce the same graph. We have some freedom in how we draw the edges between different copies, although the resulting graph's degree and girth will always be the same. It turns out that with this final step, we can exhaust all remaining vertices of degree x minus 1, adding a single edge incident to each one of them, resulting in a Hamiltonian regular graph with degree x and girth y. Now, why is it that the previous step raised the degree by 1 for every vertex of degree x minus 1? Well, before that step, in each copy of A, there were m-2 vertices of degree x minus 1. And disregarding the adjacencies pertaining to B's Hamiltonian cycle, each copy is in a sense adjacent to m-2 other copies. So we can start with copy 1 and work our way through all the m-2 vertices of degree x minus 1 in that copy, linking each one to a vertex in another copy that hasn't yet been reached by this process, exhausting the m-2 adjacencies to other copies. And then we can progress to another copy and do the same thing, obviously avoiding any vertices that were already linked in a previous step. At every point in this process, each copy has exactly as many remaining unused neighbors as it has remaining unused vertices of degree x minus 1. So when we finally run out of intercopy adjacencies, we would have raised the degrees of every x minus 1 degree vertex in the graph to degree x. After this process completes, the graph is regular of degree x. But why is it guaranteed that our graph still has girth y? This is because cycles in this graph are either entirely within one copy, which must have length at least y, or they go between copies, That is, they have at least some edges between vertices in different copies. After the step where we raised all vertices to degree x, we ended up with many more edges, so you might think that we could have produced cycles of length less than y from those edges that we added in our previous step. But thankfully, that's not the case. This is because each cycle that passes through n different copies before returning to the initial one, let's say copies c sub 1, c sub 2, and so on up to c sub n, corresponds to a cycle of length n in graph B. But since graph B has girth y minus 1, that means that n is at least y minus 1, meaning our cycle that passes through n different copies has length at least y minus 1. And from here, it's straightforward that the length will be greater than y minus 1. To see why, notice that the way we built our graph guarantees that every vertex has exactly one intercopy edge. This fact implies that for a cycle that traverses n copies, in at least one of those copies, we must have visited more than one vertex. So we can conclude that we did not form any cycles of length shorter than y by adding all those new edges in our last step. And this pretty much completes our proof. We've constructed a Hamiltonian xy graph, completing our second inductive step. And with the help of base case 2, this means that we can state that for all r greater than or equal to 2, there exists an ry graph. This completes our first inductive step, and together with base case 1, proves that for all rg greater than or equal to 2, there exists an rg graph. It can really clarify things to construct some rg graphs using the method in our proof. Let's say we want to build a 3-3 graph. How do we do it using the method of construction in our proof? To start, take the graph with degree 1 less and the same girth, and let that be our graph A, the one we make copies of. And then take the graph with degree equal to the order of A, and girth 1 less, girth 2, and let that be our graph B, the one whose vertices we replace with copies of A. The 2-3 graph is the cycle graph on 3 vertices. Since it has 3 vertices, graph B is the 3-2 graph. This is the diagon with 3 edges. Next, let's replace each vertex in graph B with a copy of graph A. The subscripts represent which vertex in graph A a vertex in our new graph corresponds to. The superscripts represent which vertex in graph B a vertex in our new graph corresponds to. Now, a sub 1, a sub 2, a sub 3, a sub 1 is a Hamiltonian cycle in graph A, and b sub 1, b sub 2, b sub 1 is a Hamiltonian cycle in graph B through the edges highlighted in red. Remembering our construction, what we want to do is start in the copy corresponding to the first vertex in graph B's Hamiltonian cycle, that's copy 1, and then take the last vertex in that copy's Hamiltonian cycle and link it to the first vertex in the next copy's Hamiltonian cycle. As our next step, our current copy is now copy 2, and we take the last vertex in its Hamiltonian cycle and link it to the first vertex in the next copy's Hamiltonian cycle, where the next copy is copy 1. This completes the cycle, so we're done with these types of edges. Now, consider each edge in graph B that does not pertain to our Hamiltonian cycle in graph B. That would be just the edge drawn in the middle. For this edge, which links vertices 1 and 2, we draw an edge between some vertex of degree 2 in copy 1 and some vertex of degree 2 in copy 2, of which there's only one choice, vertices a1 sub 2 and a2 sub 2. We're done. This is our 3-3 graph. It has 6 vertices. Now say we wanted to find the 4-3 graph. We'd have to use a 3-3 graph as our graph A, and then find a graph that has degree equal to the number of vertices in A, with girth 1 less than 3. Notice that this might cause some trouble because maybe we don't know of any 3-3 graphs off the top of our heads. But we can then apply our method recursively until we get a base case, which is a diagon or a cycle graph, and then work our way upwards. For example, if we were to find the 4-3 graph using only our method recursively, then we'd find the 3-3 graph from the base cases as we just did, and let that be our graph A. And for graph B, we would need a graph that has degree 6, the number of vertices in A, and girth 1 less. That's the 6-2 graph. Since this is a base case, we're done. More generally, if we want to find an RG graph, we must first find an R-1G graph, which may itself require us to apply this method recursively. And then once we find it, which we'll call A, we must find a regular graph of degree equal to the number of vertices in A and girth G-1. We'll call that graph B. Note that finding graph B may itself require us to apply this method recursively. Finally, we apply our construction to get the RG graph. To finish the video, let's do a recap. We have a construction that works by starting from a few cases, the 2G graphs and the R2 graphs, and then progresses toward building an RG graph. By showing that for any RG greater than or equal to 2, there exists an RG graph, our construction also shows that for any RG greater than or equal to 2, there exists an RG cage. That's it for this video. Thanks for watching. If you enjoyed this video, please subscribe and click the like button. Have a great day.